basically, my talk will be similar. I mean, in concept, in some way, as previous talk, we use neural network to fit potential energy surface and other properties. And but I will focus especially on the fundamental aspects in this learning process, that is symmetry and the completeness of the system. Actually, my research interests, as Pavlo has introduced, have been focusing on the reaction dynamics simulations of gas surface interface. Those surface processes are relevant to heterogeneous catalysis and crystal growth and so on and so forth. What's special here is that we would like to know the information and the dynamics at the quantum state resolved level. So the key to extract such kind of information from theory is to have a potential energy surface. With that, we can either do quantum wave packet propagation or classical trajectory simulations. So I will focus on how to construct the potential energy surface in our systems. In some way, this system is special because we need to, first of all, consider a global configuration space, including the asymptotic region in which the molecule is far from the surface, and also the strong interacting region where the bond breaking and forming occurs. And second, we need to deal with the anisotropic molecular system in the gas phase and also the periodic condensed phase of the surface. And we would like to have a highly accurate and highly efficient potential for doing dynamics. I think most of you, I guess all of you are very familiar with the concept of potential energy surface, which is a natural consequence of the Born-Oppenheimer approximation. I will limit my talk to the ground state or adiabatic potential energy surface. I know there are many experts in doing machine learning in non-adiabatic dynamics, but in our projects, we basically use machine learning as a regression tool to fit this multidimensional function with respect to the coordinates. And the thing is that we need to consider the translational and the rotational invariance of the system of the potential energy surface, so that we typically use internal coordinates. That's a straightforward way. And but the key here is that we also need to consider the permutation symmetry of the system, which means, for example, this water molecule, if you exchange these two atoms, and you will get the same result for your potential energy function, right? So in other words, your function, no matter what kind of machine learning techniques you use, you have to preserve the symmetry before you know in the sequence of the bond distance or angles you input to the model. So we use neural networks because it's high flexibility, but like I just said, many other options of machine learning techniques you can choose, but none of them recognize this chemical symmetry by themselves. So what we do is to introduce the symmetry to the neural network or by our own way. So an intuitive way is to symmetrize the input layer, and actually you put the symmetry to the network in the beginning. And when in 2013, when I was still a postdoc in Hua Guo's group, we come up with the idea of using the global descriptors, which is so-called permutationally invariant polynomials, originally proposed by Joe Bowman for learning potential energy surface in gas phase. And this permutation invariant polynomials was generated in terms of the bond interatomic bond distances. Let me, okay, sorry. All right, so you just act your symmetry operator on a different set of bond distances, and you have you will have the PIPs, and it provides a general way to symmetrize the global coordinates. And it's very intuitive for simple systems. For example, water, you just need to consider the sum and the product of the two OH bonds, and you have the full symmetry of the system. That's very easy. But for more complex systems, even 4 atoms, then you will run into a problem if you use those intuitive terms. Let's say the sum and the product of those atoms relevant to the 2 hydrogen atoms in this system. And you will have force symmetry, which means if you exchange these 2 bonds only, you will get the same identical energy as you exchange the 2 atoms. Then to break this force symmetry, you have to introduce additional terms which lead you to the global completeness in PIPs, and this will lead to a much smaller fitting error, but the price you have to pay is to afford the large and huge number of PIPs, much larger than the number of bonds you have in the system. For example, for this 6-atom systems, you will have about 800 of PIPs. Even you have some way to remove some linear dependent terms, and then you still have to deal with hundreds and thousands of terms for a small system. So this approach has been so far applied to like 10 atoms or so. And then for using this approach in gas surface interface, we have to make additional assumptions. For example, we have to fix the surface degrees of freedom and consider the permutation in the molecule and the surface symmetry. So the largest system we have done is methanol dissociation on copper 111 surface. We will have at last over 500 fundamental invariants to consider the full symmetry of the molecule only. But if we move from the rigid surface to a mobile surface, we need to consider permutation of so many metal atoms, and that's an impossible task using this approach. So we come to a position which has been mentioned in the last talk by Professor Isayev. And we use this idea of atomistic neural network, first proposed by Behler and Parrinello in 2007. And I think the key part of here is that to decompose the total energy into atomic contributions. That's a local approximation, which has been used actually in many empirical force fields like EANN and EMT and so on. And but the difference is that you now use a neural network to represent the atomic energy and use the symmetry functions to describe the environment around this center. And of course, you have to use a cutoff function to truncate the non-ranging interaction. Otherwise, you are still considering all the information of the system. So the key here is that the interaction and also the symmetry are truncated within a local environment. So you have you can consider a much smaller system than the whole system, especially for complicated condensed phase systems. And but one of the question or the room for improvement of this method is that it's the efficiency. And here is the review in 2020 talking about the speed of the machine learned potentials. They are on the order of 10 to the -4 to 10 to the -3 seconds per atom per MD step per CPU core, which is which are about 2 orders of magnitude smaller than empirical force fields. And we observe that the cost mainly come from the computation of the descriptors rather than the neural networks. So for example, the angular descriptors in the BPNN framework actually contribute most of the time for the computation. And because it scales with respect to the neighbor atoms by the square of the neighbor atoms. And then we are inspired by the empirical force field named EANN, which use the same atomistic decomposition of the total energy, but with the embedded density to represent the atomic energy. And what we need to do is just to replace the complex functional with the neural network, and then use a better way to represent the density of the central atom. And from quantum chemistry, we know that the density is the square of the wave function of the system. So we construct the Gaussian type orbitals of neighbor atoms and square them to get the embedded density descriptor. And here we have the orbital coefficients, which can be optimized along with the neural network parameters. And what's interesting here is that if you do some math, then you will transform this kind of linear combination form to an angle and the bond and the bond angles form, which variant to this translational and rotational symmetry, and also this embedded density descriptor is much faster than the original Behler-Parrinello type of symmetry functions, because now we have the linear scaling with respect to the neighbor atoms. And you can also choose other type of orbitals as the atomic orbital to construct the density descriptor. For example, if you choose the switching function, then you can you no longer need a cutoff function actually to truncate the interaction. Then you will further speed up the computation of the descriptors. And according to our test, our EANN model or this PN model is much faster than other popular machine learning potentials when achieving similar or comparable accuracy for the same system using the same data set. And it's already closing, approaching the speed of the empirical force field for those bulk systems, and also for the liquid water system. We have here we use the data from other people's work. And another problem of this high-dimensional neural network representation is that typically people are using like 3-body or 4-body descriptors to describe this local environment. But recently, a paper from Micheli-Chirotti's group demonstrated that even use such kind of many-body descriptors, you sometimes miss up some, cannot distinguish some atomic structures. For example, in this diagram, we have a methane molecule with a carbon center, and then we can immediately know these 2 atomic structures are different. But if you use only 3-body descriptors, you cannot distinguish them. That will introduce a distortion when you train in your force, and that will increase your fitting error quite much. And since our density descriptors have still this 3-body correlation form, so we cannot distinguish such kind of geometries. And not only our descriptors, but many other similar descriptors suffer from the same problem. And what we do is to again inspire from the physics or quantum chemistry. So in our expression, the descriptor is constructed by the linear combination of atomic orbitals. And this orbital coefficient is typically fixed after training and for any geometry in our original EANN framework. So, but in quantum chemistry, we know that the orbital coefficients should be also dependent on the atomic structure of itself. So we introduce this another atomic neural network to express this coefficient itself, and in an analog of the atomic energy. In such a way, we expand the information from the neighbors of neighbors, and then immediately we can distinguish the atomic structure and remove the artificial degeneracy I mentioned earlier. And what's more important is that, and interesting is that we can prove that with this kind of iteration, we can actually recursively introduce the information of all the correlations in the local environment. For example, we choose a linear activation function, and for simplicity to derive this derive how the correlations can be gradually introduced in this descriptor. And in each iteration, you introduce two more atomic orbital coefficients, and also two more functions with the internal coordinates, and eventually you will have 3 times 2 over t plus 1 minus 1 in interatomic distances, which will cover your local environment. For example, you start from this carbon atom and you connect the two hydrogen atoms by the red lines, and then you start from the 2 hydrogen atoms and connect the other 2 with the blue lines, and at last you will connect the center carbon atom with all the hydrogen atoms. And we provide an estimate of the largest of the minimum iteration step that you need to achieve the local completeness. And immediately, many of you may already realize that this is a message passing form, as already introduced in the last talk by Professor Isayev. And I think the key here we want to emphasize is that typically the message passing neural network was inspired by the graph neural network in computer science, and it's physically less intuitive. But in many cases, for example, the very early example of this type of neural networks, the SHINET, they use just Gaussians to iteratively incorporate the information from neighbors, and then to represent the atomic structure. But we can show in some cases, for example, this massive molecule with this configuration, then you can show if you have a truncate cutoff distance at for example 6.5, then you will miss some of correlations in such a way. Sorry, and some of the atoms are not correlated, and our model actually connects the message passing concept with the conventional atomic descriptors. So here is the numerical test of our model, and on the left we show the results of the descriptor itself with a linear regression without using neural networks, and our results with the t equals 2 with 2 iterations actually perform much better than using t equals 0 and the previous 3-body and the 4-body descriptors. On the right, we show the full neural network models that with t equals 2 or already converge in terms of the fitting error, and it's much better than the original 2-body and 4-body descriptors. And our model is also tested against the molecules and also the periodical systems. Especially, I would like to say even such kind of molecular the MPNN models can apply to periodical models, because there are so many atoms around a local environment, so its correlations are limited, as I showed you earlier. So the errors of the such kind of models are limited, and because we have now passed message, this message passing form actually incorporate the information, some of the information near the local beyond the cutoff sphere to the atom center. So it's in principle to use a smaller cutoff to achieve the similar symmetry. And when you use this a large cutoff, then you have a better accuracy. So we test our model against 2 different set of liquid water data, and we show our better performance compared to the conventional atomic descriptor-based models. So we also developed this Pytorch-based neural network package, and publicly available recently for people using. And this model not only fit energies and forces, but also apply to dipole moments and polarizability and other properties. And if you are interested, you can check it. Do I still have time? Almost.
Yeah, yes, because it started later, so yeah.
Oh, okay. So if I still have time, I may show you some other information about the symmetry relevant to my topic today. So we can actually very easily extend this atomic expression to NER dipole moment. What you need to do is just to replace the atomic energy with the atomic charge, and you multiply your neural network output with the coordinate vector, and you have the dipole moment vector that can be trained to the reference dipole moment obtained from quantum chemistry. And in such a way, rotational covariant symmetry is preserved. And we have used our model for learning dipole moments in some anomic acids, collaboration with Professor Jiang in our university. And but we encounter a problem when we learn the transition dipole moment. If you look at the difference, the transition dipole moment actually is not just a distribution of the charge, but the change of distribution upon the electronic transition. So, for example, if you have this NMA molecule, which the transition mainly is dominated by the CONH4 atoms in this planar geometry, then you will have implanar transition and the perpendicular transition for different electronic characters. And the practical direction of this transition dipole moment vector is actually undetermined for an arbitrary geometry. And for planar molecules, if you use this expression, that will be always in plan with the the vector will be always in the molecular plan, but you cannot predict the perpendicular component. So we try to again borrow the idea from the physics. You can introduce 3 different neural networks to represent the dipole moment vector, and the first 2 are just the 2 different output of a same neural network, and you take a cross product to get the 3 the third vector, then you form the three basis vectors, and that will allow you to know the direction of the practical transition dipole moment in any way. So once we use this three basis vector approach, then we can learn both n pi and pi pi transitions quite well. And with this transition dipole moment, then you can do spectroscopy simulations from amino acids to the protein spectrum, and we get a very good agreement with the quantum chemistry results. So with this, I would like to end my talk, and here are some take-home messages. So we need to consider symmetry and the completeness in order to develop accurate machine learning models for potential energy and also for molecular properties. And we introduce this symmetry and completeness in a physically inspired way. And we also introduce a general way to adapt conventional atomic descriptor-based models to have a message passing form, and we show how the local completeness can be achieved by this kind of treatment. And I would like to thank my group members, especially Yaolong Zhang, who did most of the work, and Hu Ce and Junfan did some tests, and also thank my collaborators and the funding agencies for their support. And thank you all for your attention.